Welcome to the channel. This is Professor Harikrishna, Department of Chemistry, SDC College, Kola. So, we know that in the field of chemistry, our main motto is to learn about one important thing, that is about the reactivity of the reactions. So if we come to the reactions, we can perform the reactions either in an open vessel or else in a closed vessel, or we can go with an isolated vessel also. But if you consider a reaction that can be taken place in a closed system, so if you consider the reaction that consisting or that taking place in a closed system, we can notice that when the reaction is started, the concentration of reactants will slowly decreases and that of the product will increases. So when you analyze the course of the reaction, you will come to know that at one particular stage, let me tell you this way, when the reaction is allowed to proceed, the rate of the reaction will goes on decreasing because of it is concentration dependence. When the concentration of the reactants will decreases, obviously the rate of the reaction also decreases. But do remember, the reaction is taking place in a closed system. So when you analyze the reaction during the course of the reaction, you will come to know that at one stage, the concentration of the product will again start to diminish. It will again start to decrease. But in the beginning of the reaction, you can notice the concentration of the reactants will decreases and that of the product will increases. But at one stage, when the reaction reaches to one stage, the concentration of the products will again start to decrease. That means the reaction has started to take place in backward direction. That means in closed system, the reaction is reversible in nature. In the sense, it is taking place in both forward as well as in backward reaction. So, when reaction is started to take place in both forward as well as in backward direction, we can notice that the concentration of the reactants also somewhat will get vary and that of product will also get vary. But if you allow the reaction to proceed further, you will come to notice that at one stage the rate of the reaction will become zero. But one question comes to our mind, why the rate of reaction becomes zero? That means, is that reaction, there is no reaction is taking place? Obviously not. There is reaction, both forward as well as backward reaction. But in what speed the reactants are converting into product, in the same rate the products are converting into reactant. Both the reactions are taking place in the same rate and they reach at one stage where the rate of forward and the rate of backward reactions are exactly equals to each other, and at that stage the concentration of the reactants and concentration of the products will remains the same, and that stage is actually called as the state of equilibrium. State of equilibrium. And in today's session, to the word of equilibrium, we shall attach the word phase. So that means the topic of our discussion is phase equilibrium. So the equilibrium of the reaction, we have given the meaning of the equilibrium, and that equilibrium, for the word equilibrium, we have attached the thing phase. That means the physical states of the constituents that are present at the state of equilibrium. So we are interested to discuss about the content that is pertaining to phase equilibrium. So before going to the core concepts of the phase equilibrium, we need to understand the two simple types of the state, that is equilibrium. So now we shall look over about the two types of the equilibrium. The first type of equilibrium is homogeneous equilibrium. The name itself telling you that it is homo, that means of the same type. So if you consider a very simple example, say hydrogen gas, which is combining with iodine gas, and that can change into hydrogen iodide. As well, the hydrogen iodide can turns back to give hydrogen and iodine once again. So here you can notice hydrogen is in a gaseous state, iodine is in a gaseous state. Both are interacting to give hydrogen iodide, which is once again in the gaseous state, and you can notice both reactants as well as products are existing in the same phase. They are existing in the same physical state, and that kind of equilibrium is called as homogeneous equilibrium. So here you can notice there are two reactant molecules and there are two product molecules. That means the number of reactant molecules and number of product molecules are same. But if you consider one more example, sulfur dioxide, when it is oxidized, that is combined with oxygen gas, reversibly it will changes to give sulfur trioxide. So if you want to balance this equation, 2SO2 plus O3 so as to give 2SO3. You can notice 2 is a 4 plus 2, 3 is a 6. And there are two sulfur atoms and there are two sulfur atoms. The law of conservation have been satisfied. But notice here we have 2 plus 1, 3 reactant molecules. But here we have only 2 product molecules. So either of the cases are possible in case of homogeneous equilibrium, provided sulfur dioxide is a gas, oxygen is a gas, and sulfur trioxide is also a gaseous material. So both reactants and products are existing in same physical state. So it comes under homogeneous equilibrium. So in this way, you can give a simple examples for homogeneous equilibrium. So if you go with the second one and the most important one for the topic of phase equilibrium is heterogeneous equilibrium. As the name itself telling you, it is hetero in the sense different. So hetero, it's different, genius in the sense phase. So we'll be having different phases of the constituent materials that are existing in the state of equilibrium. So let us consider one simple example such as decomposition of the limestone, that is calcium carbonate. It is reversibly changes so as to give a quicklime, that is calcium oxide, and the liberation of carbon dioxide. And here we know that calcium carbonate, which is a solid in state, and quicklime, calcium oxide, is once again a solid, and carbon dioxide is a gaseous material. You can do the comparison. Here both reactants and products are in the same physical state. But here in this case, the reactant is in the solid state, and the products, there are two products. One product is in the solid state and other product is in the gaseous state. So we are not having the same physical state for both reactants and products, and we cannot consider this under homogeneous equilibrium. This is in particularly heterogeneous equilibrium. And we can take one more example. Let us consider the very simplest salt, that is ammonium chloride, which is a solid in state, which is reversibly decomposes so as to produce NH3 ammonia, which is a gaseous material, and HCl, once again it is a gaseous material. And here you can notice in the first example, we said the solid reactant on decomposition give one solid product and one gaseous product. And here you can notice one solid reactant is producing two gaseous products, and the physical states of reactants and products are different. So it comes under heterogeneous equilibrium. And while analyzing the whole and soul characteristic properties of heterogeneous equilibrium, a very famous scientist by name Gibbs noticed the factors that are influencing the heterogeneous equilibrium, and he noticed many factors and many conditions that are compulsorily required in order to specify the state of a system which is existing at equilibrium, and he actually developed a simple important topic that is nothing but phase equilibrium. And in order to understand the phase equilibrium, Gibbs proposed enunciated phase rule. Gibbs proposed phase rule. And the phase rule which is proposed by Gibbs is very much important in order to understand the impact of the various factors on the state of equilibrium in terms of the phases of the constituents that are forming, that are present at the state of equilibrium. And according to the phase rule which is proposed by the Gibbs, it is F is equals to C minus P plus 2. This is the phase rule proposed by Gibbs. And here we shall see what are the exact meanings of the terms which are present in phase rule, that is F, C and P. And here P is nothing but number of phases that are present at the state of equilibrium. C is the number of components present at the state of equilibrium. This is the most important factor. And at the last, F, that's nothing but number of degrees of freedom. This is actually the most important one that comes in phase rule. So here I said number of degrees of freedom, in the sense, in order to specify the state of equilibrium, or else let me say in this way. So how to judge that the system is present in an equilibrium? How to judge? It's a very simple way. We can notice the constancy of the parameters such as pressure, temperature, concentration, density, color, whichever is suitable for a particular case. By noticing attainment of constancy of either of these factors, we can say that state is existing in equilibrium. The system is existing in equilibrium, or the system is at the state of equilibrium. So in order to understand the core concepts of the phase equilibrium, or in particularly speaking phase rule, we need to understand the exact meaning of these three terms, that is phase, components and degrees of freedom. Okay. So with that, in order to understand the core concepts of the term phase equilibrium, we need to understand the components that are present in the phase rule, that is F, C, P, that is phase, components and degrees of freedom. So among the three factors that are present in the phase rule, first we should consider the first term, that is phase. And here the actual meaning of the phase is, if you consider a system which is existing in the state of equilibrium, and if you notice the constituents that are present at the state of equilibrium, the number of independent constituents that are distinct from one another, or else let me say in this way, the distinct part of the system among all the constituents that are present at the state of equilibrium, the distinct part of the equilibrium which is completely different from that of the remaining parts, and that part, if it is possible to separate mechanically, then that each distinct part of the system is simply considered as phase. So that means each distinct part of the system which can be separated from the other parts of the system, that means the constituents of equilibrium, through mechanical methods. Then each part of that system, that is equilibrium, is simply called as phase. So let us consider one simple example. Say if you consider water that can be present in the form of ice provided in the solid state, and that will be in the state of equilibrium with the liquid state of the water, and that is once again in equilibrium with its vapor state. So ice is in the solid form, liquid, vapor. All these three states are exactly in equilibrium with each other, but ice is completely distinct from liquid and vapor. Liquid is completely distinct from ice and vapor because it is in the solid state and it is in the gaseous state. Vapors, though they are in the equilibrium, it's completely distinct from these of two. So, ice is a distinct phase, liquid is a distinct phase, vapor is a distinct phase. So, we can say here we have totally 3 phases. And if you consider one particular example, say decomposition of the limestone, that is calcium carbonate. Calcium carbonate will decompose us to give, we know that, quicklime and carbon dioxide. So though calcium carbonate, it's a solid state, quicklime in the solid state, carbon dioxide is in the gaseous state. But you can get confused. Here calcium carbonate is in the solid state, quicklime is in the solid state. So we can say both of these as single phase, but actually not. We said each distinct part, there should be different from each other. The different components should be considered as different phases only. So here calcium carbonate is one distinct part and calcium oxide is other distinct part, carbon dioxide is other distinct part. So totally we are having 2 solid phases and 1 gaseous phase. So totally we are having 3 phases in this particular system. And if you consider one more, say the decomposition of ammonium chloride. Ammonium chloride splits to give NH3 and HCl. So NH4Cl is in the solid state, NH3 is in the gaseous state, HCl is in the gaseous state. And here you can say we have 2 gaseous phases and 1 solid phase. Not. We have 1 solid phase and 1 gaseous phase. How? The logic is the gaseous materials are completely mixable with each other. We cannot differentiate when 2 gaseous materials are mixed with each other. We can't say this is the particle of one gas and this is the particle of other gas. It is not possible to judge. Right? So, this whole mixture will be taken as one phase and this is the other phase. So, totally we are having 2 phases. And if you consider one more mixture of carbon tetrachloride and water. We know that carbon tetrachloride is an organic liquid and water. They are completely immiscible to each other. So, we shall apply the concept phase. Each distinct part of the system, that means they are immiscible to each other. Though they are liquid in state, they are not going to mix with each other. They form distinct layers in the system. So here, the mixture of carbon tetrachloride and water will once again form 2 phases. So we should go with distinct parts of the system. So hope you understood how to judge the number of phases that are present in a individual equilibrium state. So the one thing we are supposed to remember is it should be a distinct part and it can be separated from other parts by any mechanical method. So these are the simplest examples for the term phase. And now we shall go with the second part, that is components. As I told you, compared to the phase, component is a very important factor and a phase role. So what is the exact meaning of component then? A component in the sense, if you consider a state of equilibrium, here, if you notice the constituents that are present in the equilibrium state, each component which is having completely distinct composition. I repeat, if you consider the state of equilibrium and the constituents that are present at the state of equilibrium, each distinct composition of the equilibrium will be considered as one component. I repeat once again, each distinct composition of the equilibrium state, the constituents of the equilibrium, will be considered as one component. So let us say the exact meaning of component: each distinct composition at the equilibrium is simply considered as component. So if you consider the same thing, that is the equilibrium which is framed between ice and liquid, that means of water. So what is the chemical composition of ice? Water itself, though it is in the solid state. And what is the physical, the chemical composition of the water? Once again, it is H2O. Though they are present in different physical states, the chemical composition of both the components are same. So, though there are two phases, we used to say it is a one component system. Similarly, if you consider the sulfur system, sulfur will exist in four different phases. Say, rhombic sulfur, monoclinic sulfur, liquid sulfur, and the vapor form of sulfur. So there are four different phases: rhombic, monoclinic, liquid, and vapor. Each one is completely distinct from each other. So we used to say there are four phases for the sulfur system. But if you go with the chemical composition, sulfur, S4, or else you can say simply say S, and here monoclinic, sulfur, liquid, sulfur, vapor, sulfur. So for each phase, the chemical composition remains the same. So once again, it is a one component system. But if you go with some different cases, say if you consider the system of KCl and H2O, and here you can notice it's a single phase system because KCl is completely soluble in water, so you will be observing only one system only. That means you cannot notice the presence of KCl particles in the solution because being a polar material, KCl is completely soluble in water, so as to give a single homogeneous system. Each and every homogeneous system will be taken as one phase only. So the KCl and H2O will be a one phase system. But you can notice we have two chemically distinct components. That is, KCl is completely distinct from H2O. H2O is completely distinct from KCl. So here, though we are having one phase, this is a two-component system. And similarly, you can go with one more example, that is a mixture of CCl4 and water. And once again, CCl4 and H2O. This is not a homogeneous system because CCl4 is not miscible with water. So these two are completely immiscible. So here the number of phases are also equals to 2. And here we can notice two completely distinct compositions are there. So it is two component system. So in this way, we can observe the number of components that are present in each and every system. And in order to calculate the number of components present in a system, we can use a simple mathematical formula, that is C is equals to N minus E, provided C is the number of components and E is the number of independent equations that are taking place in a system with n number of constituents. I repeat, the number of components that are present in a system will be exactly equals to the number of constituents that are present in the system minus number of independent equations that are taking place in a system. And for which we shall consider some of the simple examples and we should try to calculate the number of components in a system. Okay, so we said the equation that we can use in order to calculate the number of components that are present in a system will be C is equals to N minus E. So we shall consider one simple example consisting of constituents CaCO3, CaO and CO2. These are the constituents that are present in the system, for which we can plot the simple equation that is possible at the system will be CaCO3 reversibly decomposes to give CaO plus CO2. This is the one and only equation possible with this particular constituents that are present in a system. So for which E is equals to 1, that is the number of independent equations. And if you count the number of constituents that are present in a system, 1, 2, 3. So there are three constituents that are present in a system. So we can use the equation C is equals to N minus E. So C is equals to N minus E, where N is equals to 3 and E is equals to 1. So totally 2. So there are 2 components in the system. So if you go with the one more, KCl, NaCl, H2. These are the constituents that are present in the system. So here we can draw the equation KCl plus NaCl. So here we are noticing the displacement reactions KCl and NaCl. So the cations or anions can be placed to give KCl, and once again NaCl itself. After displacement also the same components will be getting. So there is no independent equation is possible because both the reactants and products are same. So independent equations that are possible is 0. But if you go with the number of constituents that are present at the system, KCl, NaCl, H2O. So there are 3 components. So the number of components is equals to N minus E. That's equals to N is 3 and there is no independent equations. So the number of components in the system are 3. But if you consider this particular system, KCl, NaBr and H2. If you consider this system, if you go with the number of independent equation KCl plus NaBr, and here the displacement reaction can occur. So Cl will be replaced with bromine and bromine will be replaced with Cl. So we will be getting KBr plus NaCl. So we are having an independent equation. So the value of E is equals to 1. And the number of constituents that are present in the system 1, 2 and 3. So there are 3 components. So the number of components is equals to C is equals to N minus E, that is N is equals to 3 and E is equals to 1. So there are 2 components in the system. And let us consider the other one, KCl, NaBr, KBr, NaCl, K plus, Na plus, Cl minus, Br minus and H2. A very big system, right? So for which we shall try to draw the independent equations that are possible. So first, KCl plus NaBr will reversibly change so as to give KBr plus NaCl. This is one independent equation possible, but still you can notice we are having the ionic forms also. So KCl will split to give K plus and Cl minus, and NaBr will split to give Na plus and Br minus. KBr will split to give K plus and Br minus. NaCl reversibly splits to give Na plus and Cl minus. So totally 1, 2, 3, 4, 5. There are 5 independent equations that are taking place in this particular system at the state of equilibrium. So the value of E is 5. And now we shall see the number of constituents that are present in the system. 1, 2, 3, 4, 5, 6, 7, 8 and 9. So N is equals to 9. So we can calculate the number of components, that is C is equals to N minus E, that's equals to N is 9 and E is equals to 5. So 9 minus 5, that's equals to 4. So the number of components in this particular system is equals to 4. So in this way, you can easily calculate the number of components present in any system just by knowing the number of constituents and the number of independent equations that are taking place in the system by using the equation C is equals to minus E. And that's about the second component, the second parameter that comes in the phase rule, that is component. Okay. So till now we have given description regarding the 2 parameters that comes in phase rule, that is phases and components, and now we shall go back to the last component and a very important component, very important parameter that comes in the phase rule, that is F, nothing but degrees of freedom. So what is the degrees of freedom? It's the most important one. So degrees of freedom is simply nothing but, so we said, if you consider a system, there will be certain definite number of phases and there will be certain definite number of components. But in order to specify that particular system, how many independent variables are required? Those independent variables that are required to specify the state of a system, specify the equilibrium system, are simply regarded as degrees of freedom. The equilibrium state of a system can be specified by only one parameter. That means it may be pressure, it may be temperature, it may be concentration, it may be color, it may be density, it may be anything which is suitable for that particular case. What number of parameters, strictly speaking, independent variables that are required to specify the system, that number of variables are strictly called as degrees of freedom. So we can simply say the number of independent variables that are required to specify the system at complete internal equilibrium will be simply called as the number of degrees of freedom. So let us consider 1 or 2 examples in order to specify how many degrees of freedoms are required for a particular system. So let us consider the equilibrium that is existing between ice and the liquid state. Or else let us consider ice and vapor state. So if you consider this particular equilibrium, here there are 2 phases and 1 component. But here we can use either temperature and pressure, or pressure and volume. So either of the one can be used, either of these 2 parameters can be used to specify the system. But in actual sense, in order to specify the system, any one parameter is required, because if you are specifying the temperature, obviously automatically pressure will be notified. If you are specifying the system by using pressure, automatically the temperature will be notified. So either temperature or pressure, any one parameter is enough any one variable is enough in order to specify the system. Therefore, the number of degrees of freedom for this particular system is equals to 1. And if the number of degrees of freedom for a system is equals to 1, we used to call that system as monovariant, or you can also call it as univariant. And similarly, a system can have 2 degrees of freedom, a system can have 3 degrees of freedom, or else a system may not have any parameters, means there will be no degrees of freedom also. If you consider the equilibrium of ice, liquid and vapor, provided all the 3 states are existing in the state of equilibrium, means all these 3 phases will be coexisting at a point, and at that particular point all are coexisting, no need of specifying the system, to say no variable is required to specify the system. In such case, f is equals to 0, and that system is called as invariant. So in this way, if the number of degrees of freedom is equals to 1, that will be called as monovariant. If the number of degrees of freedom are equals to 0, then we call the system as invariant. Similarly, if the number of degrees of freedom f is equals to 2, we call that as bivariant. So this is the way we can determine the number of degrees of freedom by knowing the number of components and number of phases. By knowing the values of number of components in a system and number of phases in a system, it is possible to calculate the number of degrees of freedom. And that's about the basic stuff pertaining to the phase rule. Thanks for listening to the class. Thank you very much.